Hi everyone, welcome to the first webinar of the Power and Energy series. Today, the first webinar is focused in the operation of distribution networks, considering the integration of distributed storage and also smart transformers, where we will look specifically also to the islanding operation. So me and Justino, we will present a set of new control strategies and tools that can improve the resilience of the distribution network and also enable islanding. I will start with a brief introduction to this webinar series. So our goal with these webinars is to discuss new ideas, to present you some of our work and our results regarding the energy system of the future. However, we would like also to challenge you to participate and to present with us your work and your ideas. So please, if you want to participate on these webinars, please send us your proposal to the email that you see on the slides, and we will gladly include you on one of the sessions and prepare with you the discussion. So you can also find all the details in the website regarding future sessions, and also information from and the presentations from the past sessions. So I will start first by presenting to you a set of new tools for the network planning and operation in real time of distribution networks, considering the possibility of islanding operation. These tools were implemented in the context of European Project Sensible, and they were tested both in a laboratory and also in a real medium voltage feeder. So flexibility is key for the operation of future distribution networks, integrating a large share of renewable energy sources and also electrical vehicles that in one hand can also provide this flexibility to systems, so the new distributed energy resources can provide new services to the distribution network, but this flexibility also comes from the active control of distribution network assets through advanced network applications and also distributed automation. Talking in detail regarding the storage devices, the integration of distributed energy storage can bring a large number of benefits from the building to the community until the distribution network. And focusing today in the distribution network, we can, in the first place, increase the capacity of integrating renewable energy resources that are variable in nature, increase power quality and the security of energy supply, also through the control of the storage power electronic interfaces, and we can also enable the autonomous operation of parts or specific islands of the distribution network, integrating these kind of resources. However, this autonomous operation can be quite challenging, where we require specific voltage and frequency regulation strategies that are usually provided only by conventional generation. So in this case, for these small islands, we need to consider advanced control strategies of the distributed energy resources to provide voltage and frequency regulation. So based on the microgrid concept, we can adopt this multi-level control architecture that combines local and centralized control strategies. So basically at the local control level, so we are talking about the distributed energy resources, power electronic interfaces, we can find power active and reactive power control, and also voltage and frequency regulation strategies that are implemented locally at these power electronic interfaces, and then they will be combined with it can be distributed, but also centralized control tools that can coordinate the action of the different resources. So we can combine the control of the distributed storage devices also with the renewable energy sources and also with controllable loads. So to provide this coordinated control, we need an high-level supervisory management system and also algorithms that are able to look at the future and the current network operation status and define the most adequate control strategies to ensure a secure islanding and also a secure islanding operation. So we developed this tool that tries to ensure the effectiveness of the control strategies and how ensuring that we have enough storage capacity to provide frequency and voltage regulation, and to do that, in order to do that, we will try to define the best control strategies of the grid supporting devices, such as other flexible loads or even smaller storage devices that are connected to the system that can support some part of the loads or even charge during some time if we have a lot of renewable energy sources, to try to avoid the discharge of the grid forming storage devices. So we developed what we call this short-term emergency planning tool that, based on the forecast for the next hour, tries to dispatch all the resources of the microgrid and the distribution system to ensure a secure islanding, and then to ensure that the system is able to operate islanding during a given time. Okay, in this case, we consider an hour. So the tool was tested in a real demonstration pilot, as I said, in the context of European Project Sensible. And you can see on your right side the real medium voltage pilot system that consists of a medium voltage consumer and two public distribution, low voltage distribution networks. And we have here two main storage devices with grid forming capabilities, so they are able to ensure a landing operation of these low voltage networks. So in this case, we have here a storage device and also a bigger one for the medium voltage consumer. And we have, in the case of the public low voltage distribution network, we have here also smaller units that provide support to these main grid forming units. So this system, we can create here two low voltage islands, the medium voltage consumer and this low voltage public distribution network, or we can island at the medium voltage level and have this medium voltage island supported by the different storage devices. And how this is ensured the control of all these devices by the management and control architecture that you see on your left, that basically is composed at the local level by the smart meter device, that monitors both voltage and the energy consumption profile every 15 minutes and send it upstream. Then we have here the controllers for the storage devices and the controller at the medium to low voltage substation that collects all the data from the smart meters and also ensures the control of the devices according to the set points that are sent by the high-level management tools. In this case, the short-term emergency planning tool was implemented where you see here in yellow the DSO preventive management tools. So all this data is exchanged in an horizontal manner by this IoT data exchange platform that allows us to collect data from the market, from the network, from the forecasting tools, and also publish our results for the fields to implement that the storage devices levels. But first, before going to the pilot, we first wanted to validate the control strategies and the tool in the laboratory. And to do that, we used our powered hardware in the loop test setup, where we simulated and modeled here the pilot network in the real-time digital simulator, and also some of the larger storage device units that provides the grid forming capabilities according also to the manufacturer models. And we add here one of the grid supporting storage devices that we dispatched and was connected to the real infrastructure of the laboratory. So we wanted, as I said, in the first place to validate all the local control strategies for voltage and frequency regulation, and then also test the results and the impact of the dispatch strategy on the stability of the microgrid. So we did it, and you see here the results. We have here on the bottom the microgrid frequency, and you can see the first transient is related with the islanding transient, and the smaller ones are related with the dispatch of the battery energy system grid supporting units. That will, in the first place, some of them are charging in the beginning of the landing operation, and then to be able to discharge in the when the load is higher. And we can also show you here that the algorithm is able to adapt it in real time, considering the error of the forecast regarding the real-time data that we collected from the field. So we will dispatch every 15 minutes this strategy to ensure that we maintain the balance. So the aligning was also tested in the real field, and we tested both the low voltage island and the entire medium voltage feeder. And as you can see on your right, we were able, during the islanding time between these red lines, we were able to maintain a stable frequency and also a stable voltage. There were no big transients. The network was relatively balanced and with a low load. But of course, we are talking about real clients, and real consumers, so we needed to maintain quality of service, and this was possible in islanding and with the tools running. Okay, so the real-time demonstration shows the feasibility of this islanding operation. But in order to adopt this kind of operation, we need a long-term assessment tools that, in one hand, are able to calculate and to determine the benefits for the distribution network, in this case in terms of reliability, and on the other hand also study the impact that this kind of strategies has on the battery lifetime. So we also developed a long-term assessment tool that is able to simulate both of these things. So we are able to assess the impact on network reliability regarding the common reliability indices, and then Also estimates the impact that this has on the battery lifetime with the mean number energy and frequency of charging and discharging cycles. And also estimate what is the impact that these kind of strategies could avoid the curtailment of some of the renewable energy sources, because in the tool that was developed, we are able, through a Monte Carlo simulation, to in one hand consider the storage device control strategy to support the network. So we are able to simulate the battery energy system operation plan, considering the variability of load and renewable energy sources, and at the same time simulates the outage related to the network assets that causes the low voltage and medium voltage network islanding. And we did some simulations for a number of scenarios, considering the real pilot conditions, but also some futuristic scenarios, considering a large-scale integration of renewable energy sources, where the storage will, of course, have a bigger impact. And we can show from the results obtained that, in fact, and as expected, we are able to reduce SID in terms of 1.3 hours per year, and decrease the energy not distributed in 2 megawatts per year. Of course, this will depend on the kind of failures and the type of network that we are considering, and also the load and the renewable energy sources integration scenario. Okay, so this was the work that we did for this kind of improving the resilience of the distribution network, and based on the possibility of operating islanding. And now we are, based on that idea, also trying to continue the work on a new project, which is called Universal, where we are trying to exploit the flexibility of distributed storage and other distributed energy resources by defining new grid services for the distribution network, and at the same time develop new tools that can transform distribution network operation in a more predictive and resilient way. So when we talk about flexibility services and grid support services for the distribution network, we are talking about congestion management, voltage control, and reactive power control, but we can also talk about additional services such as voltage balancing for the case of the low voltage network, or even in a more long-term services for asset management and investment deferral. And to improve the resilience, we could consider even services as intentional islanding and capacity management, more focused on giving support to the network during outages. And this can be provided by the different distributed energy resources in different ways, considering their limitation and that characteristics. So we are trying to develop this flexibility toolbox that somehow considers this standardized flexibility service for the distribution network, and also aligns this with the characteristics of the different distributed energy resources technologies. So, and then when we talk about these new generation of smart grid tools, we are considering preventive distribution management tools that can forecast and identify possible technical problems and take preventive measures to avoid it, including the network reconfiguration, but also the use of the flexibility services. But when looking also to the resilience, we want to improve the self-healing capability of distribution network through distributed control strategies that can somehow explore this idea of the dynamic islanding. So the to define islands according to the automation and to the resources available in the network. And to do that, we need adaptive and more flexible control and protection systems. And from the planning perspective, of course, the tools have to evolve to incorporate what we think is the resilience and to quantify the resilience of the system. It should be able to assess the system vulnerabilities and to really integrate these new services and these new automation strategies in the planning tools of the network. So to conclude, we have showed that the integration of battery energy storage systems can increase distribution network flexibility and resilience against unplanned failures, but we need these new planning and real-time operation strategies to be implemented. And we think the resilience will be a very important criteria for both the operation and long-term planning of distribution management tools. So thank you very much for listening. And please, if you have any questions.
Hello, everyone. Again, thank you very much for attending this webinar. And I will continue in the context of distribution grids with energy storage and smart transformers. But now I will present a more specific work related to the integration of smart transformers in the distribution networks. This work is named Fault Right-Through Strategies for Grid-Tied and Grid-Forming Smart Transformers, suited for islanding and interconnected operation. The motivation of this study to use the smart transformer in distribution networks is the expectation that large portions of renewable energy sources, electric vehicles, and energy storage systems will be integrated in the future. And this will require improved controllability and observability in the distribution networks. Among all the possibilities, the smart transformer is a possible technical solution to enable the aforementioned controllability and observability in distribution systems within the smart grids domain. It is basically a solid-state transformer, but focused on advanced monitoring and control functionalities for distribution grids. In order to show the potentials of this solution, I enumerated some functionalities that can be attributed to this equipment. One of them, which is already present in the traditional equipment, is the galvanic insulation, always needed for safety reasons. And on top of that, we can also have voltage control and reactive support. And contrary to the traditional low-frequency transformer, the smart transformer can control the voltage in their terminals independently. It can also integrate storage and also use the same storage for inertia emulation using the energy available. It can also perform frequency support using the energy storage or controlling the power in the low voltage network. It can also perform independent frequency regulation. It can regulate the frequency in the low voltage network independently of the frequency in the upstream system. It can be useful to use this quantity as a regulation instrument. And of course, it can integrate hybrid AC/DC networks, which is arguably one of the most important features of the smart transformer. It is possible because the smart transformer offers DC connectivity, which can be very useful for integrate directly DC resources. And finally, I have here the islanding operation. Since the smart transformer can integrate storage, it can operate in island mode its own distribution networks in case of outage of the upstream power system. However, the smart transformer is an electronic power device, and because of that, it has no inherent fault right-through capabilities, which is something that the traditional low-frequency transformer don't have concerns about. So we need to develop advanced functionalities to provide these capabilities to the smart transformer. We know that if we integrate if we integrate storage with the smart transformer, we can simply island the distribution networks, and the fault right-through capability can be not a big deal. But we have the possibility of don't having that storage. So if we don't have the storage, the grid, in the case of a grid-tied smart transformer, we need to implement these fault right-through capabilities in order to ensure the continuity of service and to mitigate the adverse impacts of fault disturbances in the smart transformer's distribution network. Another situation is if we want to use a grid-forming smart transformer to support a medium voltage network during the disturbance. In this case, it would be in island mode, of course, but nevertheless, we would need to ensure that the grid-forming smart transformers, namely its medium voltage inverter, have fault right-through capabilities to survive to the voltage sag before transit to a small portion of the medium voltage network to islanded mode. So it is in this context that I developed this study, and accordingly I studied these two cases, which is a case where we have a grid-tied smart transformer without local energy storage available, and the case where we have a grid-forming smart transformer and we want to use it to support an unplanned islanding of a small section of the medium voltage AC grid where the smart transformer is connected. In order to do so, some computational models were developed, but we don't have space, we don't have time here to describe them in detail. So I will focus on the strategies for the fault right-through. But I will make a brief mention to the models. I would say that the DC-DC stage for both grid-tied and grid-forming smart transformers use the same model. The same for the low voltage inverter in both smart transformers. And the main difference is actually in the medium voltage inverter, where in the grid-tied smart transformer, the inverter controls the output current, while in the grid-forming smart transformer, it controls the magnitude and frequency of the output voltage. Talking now about the proposed fault right-through strategies, I will start with the one developed for the grid-tied smart transformer. It is basically a control layer which acts on the low voltage inverter and in the isolated DC-DC converter controllers. And since no local energy storage capacity is available, this strategy exploits the voltage sensitivity in the hybrid AC-DC distribution network to regulate its net active power. So it does so by regulating the voltage in the DC bus, in the low voltage DC bus, and also in the magnitude generated for the low voltage AC grid. Further, we implemented also some models for some distribution networks comprising PV generation, EV charging, and other loads as represented here. The idea is all of these devices are sensitive to the voltage. And if you reduce voltage on those grids enough, we can reduce also the power both consumed or generated. So the strategy basically consists in three elements. We have a feed-forward control, which basically provides a fast reaction to voltage sags as a function of the magnitude of the medium voltage AC in the DC network. Then we need to remove the steady state current error in order to ensure that the current limits of the medium voltage inverter is respected. And because we need to optimize the power transfers, because sometimes the power curtailment may be superior to what is really needed, we have this third element which maximizes that. So in order that we ensure that we only curtail the power that we really need to curtail. Now about the grid-forming smart transformer. The proposed strategy is located in the current limiter, which is embedded in the medium voltage inverter. And it exploits the fact that the average current flowing through the medium voltage inverter is determined by the voltage drop in the inductance of the coupling filter. So the rationale is to exploit this to ensure that the current limits of the medium voltage inverter are respected. And of course, in this case, it relies on the local energy storage system to ensure that the power balance is preserved. This method also relies on three components, but their function are quite different. We have a voltage phase compensator, which acts on the phase shift of the voltage drop in the coupling inductor, and is responsible to regulate the active component of the current. Then we have the voltage magnitude compensator, which acts on the magnitude of the voltage drop in the coupling filter, and is responsible to regulate the reactive component of the current. And then we have a virtual impedance, which complements the action of the previous two. And it's very useful in the first moments after the occurrence of the voltage step, falling or rising, where the demanding controllability is more critical. So to test these developed strategies, a test scenario was modeled. So this is a small network. It was considered, which comprises two smart transformers, a grid tied and a grid forming, each one with its hybrid AC-DC low voltage network, which is the same for the two. And here we have some important characteristics of the model smart transformers. Then the idea is to simulate a fault in the upstream system and after a while open the breaker. And the idea is to verify that not only the grid-tied smart transformer can survive the fault, but also that the grid forming can support the subsequent islanding of the network. To evaluate the fault factor strategy for the grid-tied smart transformer, 10 scenarios are considered: a net generation scenario and a net load scenario, each one with 5 fault impedance scenarios. At first, there is no disconnection from the main power system, and the fault clearing time is 400 milliseconds. For the evaluation of the grid of the fault right-through strategy for the grid forming, two phases were considered. So in the first phase, a three-phase symmetrical voltage sag in the upstream system occurs, and there is no disconnection from the main power system. But after 400 milliseconds, the voltage sag remains active and the three-phase breaker is opened. So in order to allow the smart transformer, the grid former smart transformer to support the island, the medium voltage grid in island mode. So the results are as follows. So for the grid-tied smart transformer, we have here, I don't know if I can add some way of showing this. Just a moment. Okay, in the left, we have the voltage sag profiles that were simulated for each voltage impedance and net generation and load scenarios. And as a result, we can see that the current limits are successfully preserved. And in the right side, we can see what happens in the distribution network in order to preserve such limits. And we can see that the voltage in the DC network and AC network are reduced in order to exploit the voltage sensitivity, and with that reduce the power and subsequently the current that the medium voltage inverter needs to put in the upstream system. Here we have the powers in the distribution network on the left. We can see that the power is effectively reduced both for net load scenarios and generation scenarios. And we can see in the right side what happens with the load and the generation, the PV generation. And we can see that the power is adapted to allow the grid-tied smart transformer to perform fault right through. Regarding the grid forming, we have the results here regarding the islanding process. So in both pictures, we have after the 0 seconds, we have the instant before the fault. Then we have 400 milliseconds corresponding to the fault. And after that, we have the operation already in islanded mode. So we can see that both smart transformers can survive the voltage sag and to the islanding procedure. And that is evident if we look to the grid-tied medium voltage inverter, which does not lose the connection and continues to put currents in the upstream system. Sorry, in the medium voltage network. The effectiveness of the proposed methodologies is further evidenced if we look to the waveforms of the generated current and voltages in both grid forming and grid-tied smart transformers in the instance where the fault starts and when the islanding is performed. And we can see that the distortion is minimal and that the current waveforms and voltage waveforms can be quickly adapted. So that's it. Based on this work, it was possible to conclude that the smart transformer can indeed incorporate fault fighter strategies. For the case of we have a smart transformer without storage available, we can successfully exploit the voltage sensitivity of its hybrid AC-DC network. And for the case of a grid-forming smart transformer, which we want to use to support a small section of the upstream medium voltage network, it was also demonstrated that it can successfully withstand the voltage sag in the upstream system and then transit to the island modes without power interruption. It's worth mentioning that this work was developed considering only 3-phase balanced voltage sags. And there is further work underway already, evaluating the proposed strategies for other kinds of faults. And that's it. So thank you for your attention. I hope you have enjoyed this presentation.
Okay, so thank you very much, Justino. Thank you very much, Clara, and thank you for all the participants. Please do not forget that if you wish to participate in one of our webinars as a speaker, you should send an email to energywebinars@inesctec.pt. Just to mention that the next webinar will happen in September. We will have Carla Gonçalves and Ricardo Andrade on September 14. And the topic is data science applied for the electricity market and renewable energy forecasting. So if you wish to participate in our next webinar, please do not forget to visit our website, www.energywebinars.inesctec.pt. And thank you so much again, everyone, for participating.